Alright, so in this situation, it says there's a vehicle undergoing 3 separate periods of acceleration where the driver presses on the gas pedal 3 separate times. Assume no friction and no air resistance, and driver never hits the brake, so this vehicle's speed will only increase, never decrease. We'll assume that the vehicle starts from rest at time t equals 0. Can you sketch the vehicle's velocity versus time from its acceleration versus time graph? And what top speed does the vehicle reach after 12 seconds? All right, so the times of hitting the gas are represented here by these blocks of constant acceleration. They're constant because they're just horizontal. This is going to be time in seconds. So we're talking about from t equals 1 to t equals 5. They're hitting the gas there, and their acceleration is going to be 1 mile per hour per second. And then from t equals 6 to t equals 7, they hit the gas a little harder there, stronger acceleration, 2 miles per hour per second. And then from t equals 9 to t equals 11, they hit the gas again. We want to show how the car's velocity changes with time, though. All right, so what we have here is a piecewise defined function. And we can write out what it is. All right, so the acceleration as a function of time will be defined piecewise. So you're going to have 1 mile per hour per second for t between 1 and 5. Doesn't really matter whether you include the endpoints or not here. It's just a model of the motion. Then it's going to be zero for 5 to 6. That's going to be 2 miles per hour per second for t between 6 and 7. That's 0. And 1 for 9 to 11. All right, I hope that's a clear mathematical way of writing out what's happening in the problem. We now want to anti-differentiate. Because see, we always have this stack of graphs where the acceleration is the second derivative, the velocity is the first derivative, and then the position is often the original function that we're talking about. So in this case, we're starting at the bottom with acceleration, and we want to build upwards in our stack of motion graphs. We want to find the velocity from the acceleration. And then sometimes you'd be asked to go even farther and find the position too. So you'd have to anti-differentiate twice. All right, so let's see if we can do this. And we want to come up with formulas for the velocity that would also be piecewise. We're going to start our vehicle out at the origin, which is basically at rest. because the velocity is 0. And they said that right here. Start from rest at t equals 0. So what do you think? In that first second, is our velocity going to change, or is it going to stay at rest? I mean, the car's just in park or whatever. They haven't hit the accelerator yet. So we'll just let it be 0 for a while. Now they hit the gas. So how's our velocity going to change? It's going to slope up. It's going to steadily increase. And this is velocity in miles per hour, so the units will be just 1 mile per hour there. Then we'll have 2 miles per hour, 3, 4, 5, and so on. Question is, though, how fast is our car going to end up going after those 4 seconds of acceleration are over? In order to find that, what we want to do is alright, so we're going to take an integral of the acceleration function from 1 to 5. So that's the integral of 1 dt, because that's the value that it holds during that time. But now we have to put on what are called limits. We have to go from t equals 1 to t equals 5. So see, you start here on the left and you end there. Whenever you do a definite integral, you have to pick a time range that you're going to do it for. So we want to find from 1 to 5 the integral of 1 dt. Alright, now the antiderivative of 1 is t. Alright, but after we find the antiderivative, we have to move our limits from the left side to the right side. And what this means is we're going to plug in the 5 and the 1. So what'll it be? It'll be something minus something. It's part of the fundamental theorem of calc. Okay, so when you have a definite integral from a to b, and you have a certain function, f, like little f, then you can evaluate that by doing f of b minus big F of a. But we just want to do 5 minus 1, which is 4. And it is the area under the curve. Okay, that was one of Sir Isaac Newton's great insights. You know, famous physicist who discovered mathematics of calc. He said, well, the area under the curve would have meaning in this case. It would be the change in the graph above. That's what this whole formula says. This is the change in the velocity in this case. Alright, so we want to let our velocity change nice and steadily so that it goes from an initial value of 0 up to a final value of 4 miles per hour. And as you can see, it is an antiderivative of the graph below. Like a graph whose slope is the graph below. Alright, then what's going to happen from there? At that point, we're going to hold the 4 miles per hour steady, because there's no gas being given at that time. So you're going to stay at constant velocity for a while. Alright, but then what happens? Now we got to integrate this thing. I can see that it's going to be an area of 2, but let's just make sure the calc agrees with that, right? So integrate from 6 to 7 of 2 dt. All right, that's going to be 2t as an antiderivative. Write our limits next to this line here. And then we plug in. 2 times 7 minus 2 times 6. 14 minus 12. 2. Alright, so we got to have our velocity rise with a value of 2 miles per hour. Alright, now we're up to a total of 6 for our car. So it's just going faster and faster. Here we would do an antiderivative of 0, so we would just like leave it steady for a while. And we can see that this has an area of 2. So we're going to want to let it go up by 2. But it has to take 2 seconds to do that. We're going to get up to a total of 8 for our car. Alright, find the piecewise definition of these curves. The formula that you give has to predict where the object will be located if you plug in the time t. And so this would not give correct positions. So you have to add in the right intercept that would make it correct for this curve. So if you just notice that if you were to extend this, like extrapolate it, it wouldn't actually hit the vertical axis at 0. It would hit at -1. And so that's what you have to put in as part of your formula. So now that when you plug in a time and use that formula, it will predict a spot on that curve. Let's just try, for example, a time of 3. We see from the graph that the height off the axis should be 2. Alright, so if I plug in a 3 here, does it work out? It actually does. So now it's correct. Alright, some of them are easier to find than others. Okay, so what about here? It's going to hold a value of 4 between 5 and 6. That's this segment here. It's just a constant horizontal. But now, okay, this one. I see it's got a slope of 2, so we can do 2t, but you can't stop there because you have to find the intercept. And that's tricky to do. I mean, it's really far away from the vertical, so how do you do it? Well, you could use algebra to do it. All you'd have to do is say that we know that there's going to be some intercept b here that we're trying to find. And we can plug in a point that the line goes through. Simple as that. So here's a point. 6, 4. So if I just plug that in, this is going to be my t, this is my v. So 4 equals 2 times 6 plus, that's supposed to be a b. And then just solve it. 4 minus 12, -8 is b. So now you know what the constant needs to be. Perfect. Then it's going to hold a value of 6. And finally, we'll have t plus a certain constant from 9 to 11. Just going to do that same technique. 9 comma 6 is that point. Six equals 9 plus b2, therefore b2 is -3. All done.